Okay, good morning. So today we're going to talk about multi-level modeling. Before I get started, though, it's important that I stress the importance of completing your assignments. We have about 7, maybe 6 weeks left of the semester, including the final exam period. Obviously, we don't have any exams in this course, but there are assignments you have to complete. And if you, all I ask is that you complete them, right? So my promise to you was as long as you complete these assignments, your grade's gonna be great. But if you don't complete them, then there's really nothing much I can do about them, right? So I really, really need you all to complete your assignments so we can move forward. Again, like I said, there's only 6 weeks or so left of the class. But today we're going to be talking about multi-level modeling, and I think this is an interesting topic, and it's something that wasn't one of my types of analyses that I did a lot of. I preferred some other type of analyses, which we will see that later on in a couple of weeks. Structural equation modeling, that we can do a lot of this stuff there too. But the more and more I read about multi-level modeling, the more interesting it becomes. And it's something that you should become very familiar with. So let's just start with some basics about multi-level modeling. So it's an extension of what we call traditional fixed effects models. So there's a lot of terminology in here that I'm going to cover that you have to understand in order to understand what a multi-level model is. So first let's talk about, so I mentioned it's an extension of a traditional fixed effects model. A traditional fixed effects model would be something like a regression analysis. So with a fixed effects model, there's an assumption that the model's intercept and slope are constant across different levels. They're constant, so they don't change. And levels can be a bunch of different things. It could be schools, classrooms, etc. So when we think about the effects of a variable on one variable on another variable, we're generally looking at its effects in the population at the population level. We're assuming that everybody's pretty much the same, right? More or less, except for whatever our variables are, our predictor variables are. Those are supposed to be able to explain these differences. But sometimes people are nested within groups. Like if you think about it, cultures have their own rules and their own constraints that govern behavior, and people within certain cultures are going to be different from people in other cultures, but they're going to be a lot alike within that culture. If we think of a classroom as being like a culture, right? Classrooms are governed by their teachers. And let's assume high school right now. Or even let's go down to elementary school because people tend to spend the whole day with the same teacher. So classrooms, students in classrooms are very similar to one another because of the teacher, right? So if we were to compare individuals, say on a variable like, I don't know, like happiness between 5 different classrooms, we're probably going to have different levels of happiness, and their levels of happiness are, to some degree, are governed by those cultures within those classrooms. And with traditional fixed effects modeling, we ignore that, right? We say, okay, well, the effect of, say, exercise on happiness is the same for all students, right? So if we see that a unit increase in exercise results in a 5-point increase in happiness, we assume that's the same for everybody. But that may not be a very good assumption because, first of all, there may be just baseline differences in happiness in the different classrooms. What if one of the teachers in one of the classrooms was very depressed herself all the time, and maybe her students are going to be depressed too? Versus another one, the teacher is always jolly and happy, so students are going to be happier in that classroom. So there could be baseline differences in happiness across the classrooms, right? Or the effect of an intervention of some sort may be different depending on the class and won't be necessarily constant across classes. And so when we have situations where there's people nested within units of some sort, whether it's schools, you can be nested within a school, you could be nested within a classroom, you could be nested within a classroom within a school, right? You can be nested within a doctor. Like if you're a patient of a doctor, this doctor has like 50 patients, people might differ for this one doctor versus another doctor or hospitals. There's all these different units that can influence the the direction of your results, right? Because of that nesting within that cluster. So most traditional methods do not account for these differences. And what happens when you don't account for these differences, you shrink the variability. So you shrink the variance. One thing we know about statistical analyses is that the tests that we use are usually the same. There's always some kind of model divided by an error, like the t-test, right? The t-test, you have the whatever the difference between the means of two groups divided by the standard error. So it's model divided by error. The z-test, you have the difference between the sample mean and the population mean, or yeah, difference between the sample mean and the population mean divided by the standard error, right? Again, so it's always a model divided by an error. That error term is known as a standard error, and it's a variability. It's a measure of variance, right? When people are nested within groups and they're really similar to one another, we don't account for that. We're ignoring that shrinking of the variance. When we shrink the variance, right? People are really similar, so there's less variability in those groups. When we shrink the variance, what happens is that denominator gets smaller, making the outcome larger, right? And that means we're more likely to reject the null hypothesis falsely, so that we're more likely to make what's called a type 1 error or commit a false positive result. So if we don't account for these differences, we're going to probably have a lot of type 1 errors, and we don't want that. We don't want to have type 1 errors. We want our results to be valid, right? We want to have valid results, okay? So multi-level modeling accounts for that, and we can do it in a variety of different ways. We look for, in every model, you have an intercept and a slope, right? Either we can set that intercept to be fixed, like it's the same for everybody. The intercept is essentially the mean level of our dependent variable. So we have a predictor variable and our outcome variable. Our outcome variables are dependent variable. The intercept in that model, like if we have model y equals a plus bx, where b is a slope and x is the predictor variable, that a is the intercept, and that's generally the mean of that dependent variable. Because if we're saying, well, if our predictor variable has no effect on the outcome, how do we predict our outcome? Well, it's using its mean. So an intercept is the mean, right? If we have our intercept being fixed, we're assuming that mean is the mean for everybody, right? It's going to be the same for everybody. We could relax that assumption and say, hey, we have a random intercept. What that means is that the mean itself will differ based on the different clusterings. Again, if we're talking about classrooms, we're talking about happiness, a fixed effect would mean that we're assuming that happiness is the average level of happiness applies to everybody, right? Equally, regardless of their classroom. If we relax that and say we're going to let this intercept be random, then we would say, okay, we acknowledge that there are different mean levels in the different classrooms, right? Once we do that, we can actually model it. Like we can say, hey, what predicts that difference in classrooms, right? Not just the difference in individuals, right? We can model both of those, and that's kind of cool. Similarly, we can make the slope. Remember, the slope is the parameter that relates the predictor variable to the outcome variable. We talk about this in regression. We'll say like the effect of a predictor on an outcome is such and such, like a 1 unit increase in the predictor will result in a whatever the b value is, the slope change in our outcome, whether it's negative or positive. Similar to the intercept, we can say that that slope value is constant across the different clusters, or we can say that it is random. And if it's random, it can differ across the classroom. That's a really, really cool thing. And we can assess what are some predictors of the slope as well. So we can do a whole bunch of things with random effects models. That's what's so interesting about this. Another important point that I'd like to make, because we've talked already about repeated measures designs where people change over time. A repeated measure design is kind of an extension of a multi-level model where we're looking at an individual in a given level. The individual, we consider that individual level one. And if that individual is being measured repeatedly over time, we have variation within that individual at this individual level, and that becomes a random effect itself, right? So a lot of modeling that we use that looks at repeated measures over time is actually looking at random effects as well, because people change over time too. Usually when we talk about these these multi-level models, we'll talk about, level one, level two, level three. Like, let's just do a scenario just to make this clear. Level one would be what's going on within the person, right? So again, if there's repeated measures over time, that's level one. Level two is something like a nesting within classroom, like your students nested within classrooms. That's your next level. Level three would be schools. Level four could be community. Level five could be city, and you can keep on going on if you'd like to do this. Okay. And we have ways of measuring how similar individuals are within clusters. That's something we'll talk about in a little while. It's called intra-class correlation. We can see how strongly related people are within one of these clusters. And we'll use that as a way to indicate whether or not we need to do multi-level modeling. I mean, you don't necessarily have to do it, right? But you should do it when you are worried about clustering within units. One point that I didn't bring up here is, and I should now that I think about it, is how many clusters do we need in order to use multi-level modeling? It's not something you can do with like three levels. Like say you're doing an analysis and there's three schools, and you say, well, I want to control for school. You're not going to do multi-level modeling. In that case, you're going to create a dummy variable for school, right? So you can compare school one to school two, school one to school three, et cetera, right? You're going to do that. You're not going to use multi-level modeling for that. Usually for multi-level modeling, you need something like 50, at least 50 clusters. So this is generally done when you're doing a larger study. And in public health, we might do it where we're looking either at classrooms or schools, or if we're looking at families, because people are nested within families, right? So if we have a bunch of families in a data set, then we can use multi-level modeling. But if you have not a lot of clusters, then what I would say is we're going to just do regular regression with a dummy variable for whatever our clustering variable is. Okay, so let's keep that in mind. So today we're going to work on running well, actually, before I do that, let me just show you. So I forgot to bring this up to show you this, but just so you kind of understand what these models look like, there is a nice little and I know people aren't really happy about equations, but this is your general regression equation. I know Tatiana, you saw this last night in my other class, right? So when we were talking about regression analysis, this is the actual model, not the predictor model, because you have the error term here, but here you have the individual, and then J is the cluster, right? So you have individuals and clusters. So this is an example where you have the intercept and you have the slope. This is your traditional model, right? And in this case here, you can see that these can vary. These can vary by some cluster, like say J is school or something like that, right? And here's your predictor variable. But what we can do with this multi-level model now is model these effects. So here, this is the intercept, right? This is the intercept. We could say, let's predict the intercept based on some other variable. This W variable is, right? Whatever it could be, right? Like if we're looking at classrooms, this could be something like socioeconomic status. How does socioeconomic status affect the intercept value, the average value of something in the classroom, like happiness or something like that? See, so this is what we can do. We can model this. And in this case here, because we have this error term, there is variability in this intercept. If you look at this slope here, the slope just has, some mean value, but there is no variability. We don't have an error term. And just to be clear, the error terms, see, we use them at different levels. At the individual level, we call it E sub I, right? But at this level, this is at the next level up, right? The second level, we call the error mu, right? That's just because we have to call it something, right? But here there is no error terms. This is just a fixed effect. Like we normally say, there's the effect of the predictor and the outcome is constant across the different groups. But with multi-level modeling, you can relax that as is done here. So it's relaxed and all of a sudden say, oh, okay, now this intercept is also free to vary. But in this model that you'll notice there's no predictor here. It's just saying, okay, this intercept will vary among the different groups, right? And if I wanted to, I could predict it with something as well. It's interesting how what they end up doing is they plug them all in together because we know B sub 0 equals this, B sub 1 equals that, so we can just plug it in and make a full model if you want, just have one equation. But that's basically what the multi-level model is. Okay, so it's just this taking into account of possible randomness in our parameters, right? Saying that they're not equal across all individuals. All right, so let's go ahead and run some of this stuff here. That's the fun stuff. So we're going to use one of these data sets I got somewhere from Hill, Abram, and Wright. So they examined whether providing children with a leaflet based on the theory of planned behavior increased their exercise. So theory of planned behavior is this model. I think most of you may or may not be familiar with it. It is a public health type model where we look at what's the stages of change that occur, like in trying to get somebody to change a behavior, like they might start contemplating it and eventually they'll do it, etc. Right? So there was a leaflet based on the theory of planned behavior with that increased exercise. So there were four different interventions. There was control group, a leaflet and quiz, and a leaflet and a plan. Okay, so there's four different groups here. The researchers sampled 503 children from 22 different classrooms. Well, this is, I guess it's okay. I mean, usually, you need a lot of these clusterings, right? I'd mentioned 50. I read that somewhere, but this is sufficient for what we're doing here. There's 22 different classrooms. So here the classroom is the clustering variable, right? Because we're assuming that children within these classrooms are going to be more similar to one another than they are to children in other classrooms, right? So they asked children and our dependent variables on average over the last 3 weeks, how much have you exercised, right? Here's the question. It's not really a question, it's a statement. They have to fill in the blank here. On average, over the last 3 weeks, I've exercised energetically for at least 30 minutes, some XXX times per week. So it can be 3 times per week, 4 times per week. And this variable is called post-exercise, right? All right. So I downloaded this data set already. All right, I downloaded if you just need a refresher, when you download a data set, you'll find a place to put it, right? And let's see. Well, I have it downloaded here. Let me see if I can move it. Just use this one. Let's just, can I copy it? Yeah, copy to, and I'm going to stick it in your shared drive so that you can use it as well, okay? So this is my shared file. Anything that's in my share file, you have access to. So let's see if it's in there. Here it is. Okay, so it's in there, right? And the file I'm using today is one called essential file 1.dr.sas, not this one here, just to be clear. So you can actually run these yourselves, right? You'd run it from this data file here, okay? All right. So first thing we're going to do is, let's go back to the notes here. Step one, we're going to fit an intercept-only model. Okay, this is an intercept-only model. So that means there's no predictor variable at all. No predictor variable at all, right? We do have this classroom level, right? These are the clusterings, but we don't have a random effect in here at all. So this is what we call a fixed effect model. So it means We're assuming that the intercept is the same for every group or the average level of exercise. There's no predictor, so the only thing we have here is the intercept, the average level of exercise post-test is going to be the same across those 22 clusters or those 22 classrooms. The classroom is a cluster, right? So in essence, we know we have this variable, but we're ignoring it because I don't see it in here anywhere, right? So this model is post exercise equals nothing. So that's just going to give me the intercept only. I'm going to use a method known as the maximum likelihood method, and this is ideal because what we have to do now is we're going to compare our models. We're going to see is do we really need to do a random effects model? So we're going to make a judgment. Is the model better with a random intercept than it is with a fixed intercept? So that's the first thing we're going to do. Using the maximum likelihood method, I can do this. What is the maximum likelihood method? It's when so all of these methods, whether it's maximum likelihood or something called ordinary least squares, all of these things are meant to estimate those parameters. Because I have to get an estimate for my intercept, I have to have an estimate for my slope, and this is a method that estimates it. With the maximum likelihood method, what you do is you create this model and goes, okay, how good is this model at recreating my data, right? The data that I start with. So what I'm trying to do is to maximize the probability of the observed data. So we have a data set, right? Our goal is to maximize the probability of that observed data set. So that's what the maximum likelihood method does. And it's what we call an iterative approach. So it'll keep on going, going, going until it hits some kind of a plateau. Okay, this is the best estimate of these parameters, the intercepts and slopes that we can have that'll allow us to estimate this data set. So that's what maximum likelihood does. It's pretty cool. But we're going to use this because we're going to do a test to compare the model with the fixed intercept to the model with a random intercept. And we're going to do a test for these to see if the variances and covariances, whatever we need, are significant. We're not printing any output based on the class levels. We're going to get a solution here, which is our model outcome. That's what we want. So we have proc mixed, and we can use it. We've used this, I think, for something else already. Proc mixed. You can use this for a lot of different things. So our data is this Hill data set that's under my MV stats library, which you now have access to. The method is the maximum likelihood. These are my two options. I do a class statement. The class statement just basically creates dummy variables, right? And we'll need that later, but we're not doing anything with it right now. And we're also noting that classroom itself, the 22 classrooms, is it's a discrete variable. Our model is that post exercise is equal to something. We're only checking the intercept now, and we're asking for some output. And then these are my notes. Again, remember these are notes, right? You got slash star close with star slash. This is my notes just to remind me what everything is. So you can copy and paste that into your program, but it's already here because I did it, right? So this is the multi-level model. And just to make sure everything's okay, I ran a proc contents first, right? To make sure I have everything I need, what variables are in there. I have classroom intervention, post-exercise, and pre-exercise. So this just tells me that I have everything I need. I have 503 observations, okay? Or individuals here. So let's go ahead and run the first step. So we're going to run proc mixed here, fixed intercept only. So this is what you just saw in the notes. So this is the fixed intercept model only. I'm going to run that. All right, so we get a lot of interesting output, just some confirmation that we're using the maximum likelihood method, right? This is our dependent variable. Covariance structures diagonal. Well, it makes sense because there's a matrix and it has a diagonal in it where the variances are in the diagonal. There's only one covariance parameter, and this is going to be important because parameters is one thing that was estimated, right? One covariance parameter. A covariance, you have variances and you have covariances, right? A variance is the variability of variable. Covariance is the shared relation between two different variables. or things in this case, with 503 observations. All right, that's good. So here's our parameter estimates. We have a residual. A residual is an error term, right? An error term because we have a mean level of our dependent variable, right? That's our intercept. And that intercept is, is good at estimating our outcome, right? But it's not perfect. So this is its the leftover, the remainder, right? The residual. This is significant, right? That's just telling us that that parameter is significantly different from zero. But what I really need here, and this is my estimated intercept value, right? And that's significant as well. But what I really need here is this minus 2 log likelihood value. Okay, so I'm going to compare models. And the model I'm comparing is the model with the fixed estimate of the intercept to a model with a random intercept. And I'm going to look at the parameters, and there's going to be a different number of parameters once I have the model with the random intercept to the model with the fixed intercept. So that's why I'm going to look at the number of parameters, right? Covariance parameters. The difference between those, that's going to be my degrees of freedom, right? And this minus 2 log likelihood is a really good way to estimate a difference between two models where one model is nested within another, right? So nesting means that I can change one thing in one of the models to get the other model, right? So this is what I mean here. In the model I'm going to run next, the intercept value is random. If I fix it, I say no, the variance is equal to zero, then it becomes a constant, right? So I'm fixing one thing, right? So that one model is nested, the fixed model is nested within the random model, right? By fixing one parameter, right? Saying, okay, the variance is equal to zero. So in the random intercept model, the variance is well, it's free to vary, right? So that's what I mean by a nested model. I have one model can be made from the other model really easily. When I have that situation, I can use a chi-square test and the minus 2 log likelihood difference. So that's why I'm going to tally this value one of 849.1 for this model, and then I'm going to compare it to the minus 2 log likelihood value I get from the model with the freed intercept, right? With the random intercept. And then we'll see what the difference is. And that difference follows a chi-square distribution with, in this case, it'll be 1 degree of freedom. That's because the models are nested. When models are not nested, like I'm comparing different models where I can't just derive one from the other. And this happens often when, say, you're comparing two total different ways to fix something. You can use these other ones like the AIC, the BIC. So these are better when we have non-nested models. Well, in this case, we have a nested model, so we're going to use the chi-square difference test. But you can also use these ones when we're in situations where models aren't nested, right? You think about it, there's two different ways to get from point A to B, and one way is like flying and one way is driving. I mean, they're not really nested within each other, and we can make that kind of comparison, which model is better, right? And we can use these other estimates here. Okay. All right. So, but we see the intercept is significant. Usually we don't really care that the intercept is significant, but we know it's not zero. All right. So that's the first model. All right. So let's go. So I logged everything here, right? You'll see that. My second step was to fit the intercept only model with a random intercept. So now let's look at this, the difference in the data here. All right. So I just added some stuff. I mean, everything else looks the same. This looks the same. I did add this command random, and what's going to be random is the intercept, right? So we're adding a random intercept, and our subject in this case will be the classroom. So it's going to vary by classroom. That's what we're going to do, right? So again, this is just a node, and then we're going to get some output data, which we want. The output data will be covariance parameters. So I'm going to save those estimates, and you'll see that the output is actually useful. It's beneficial, okay? So let's go ahead and run that. So this is here. Oops. I'm gonna run that. And you see also we have output data here, and we have this nice just set of data. It's the same thing that we get inside. So now we have an intercept value and a residual, which we didn't have before, right? The data gave us just the just the residual, and this is variance, right? This is variance values, right? So now you'll see here covariance parameters is two, so we had one more. So and again, I said the degrees of freedom difference was one, 22 subjects, right? Because these are the 22 different clusterings. That's different from our number of individuals here. And we get our minus 2 log likelihood is 849.09. 849.09. I mean, yeah. Just want to make sure everything's okay here. We get our estimates, which this is what you have in the output table that I just showed you under output, right? 0.02568, 0. Yeah, it's the same thing. I mean, if you want it for some reason. Oh, no, that's not what I wanted. I'm sorry. Fit statistics, I wanted the minus 2 log likelihood was 830.4. And our intercept is still significant. All right, so but I want this 830.4. So mainly I want to know, should I just leave this before I go on to the rest of my analysis? Should I leave this intercept as fixed, or is it better to make it random? So I'm going to go back here and I'm going to calculate the difference. So the minus 2 log likelihood difference is 849.1 for the model with the fixed intercept, minus 830.4 for the model with the random intercept. I get a difference of 18.7. And with 1 degree of freedom, I found the p-value 0.00015, which means it's significant, right? So how did I find that p-value? I just, went to a handy online calculator. Let's see, chi-square p-value. You find these calculators all over the place. Here's a nice chi-square calculator, and I put in, I think it was 18.7, right? 18.7 with 1 degree of freedom. Stick it in here, 18.7 for 1 degree of, you can do this many different ways. You can do it in SAS as well. And it gave me my p-value, right? 0.0000015. So that's a probability of a value this large or larger given the null hypothesis is true, right? Given the null hypothesis is true. Null hypothesis would be in this case that there's no difference between the model with the with the with the with the random effect and the model with the fixed effects. Okay, so it's different. So this is telling me I want to proceed keeping this intercept random. Okay. I can now calculate the intra-class correlation to see how related these groups are, how much variation they share within these clusters. So basically what I'm doing is I'm calculating the between variance. So this is the variance due to the intercept in this case, divided by the total variance. It's the between and the within. The within variance is the leftover stuff, right? The individual difference, right? So between would be the differences. So we can say, well, we have these different intercepts. What's our variability of that model where we allow the intercepts to differ? And then there's just the within stuff, just the individual difference. This is the only thing we had in the fixed effects model. We just had that within stuff, just the residual. So this gives me an intra-class correlation of 0.0817. It's not very high, but there's some shared shared variance due to that grouping. Okay. I mean, it's not huge, but there is some. Okay. Okay, the next step is I want to add my intervention variable in here. So my intervention had 4 different levels. at four different levels, and those four levels, well, we want to make dummy variables out of them. So we compare, let's see what the four levels were again. And I think it was leaflet, let's see, four levels, a control group. So we want to compare everything to the control group. A leaflet group, so it'd be leaflet versus control, a leaflet and a quiz versus control, and a leaflet and plan versus control. So I'm going to create dummy variables. Fortunately for us, we don't have to do much to create these dummy variables at all, just include the class statement. So that's why you see I have a class statement in here, right? I have a class statement in here because this class statement creates the dummy variables for me, okay? So here, add, where does it? Add intervention, here adding the intervention in here. Okay, so I added the intervention here. I could, and I could set the reference category, which I should do that. Reference equals one, because one was the code for the control group, right? So I'm just adding this. This is a fixed, in fact, there's going to be dummy variables. There's going to be multiple fixed effects, right? Like group two versus group one, group three versus group one, group four versus group one. Okay. And then we're keeping the intercept random. Let's take a look at this result here. So just to be clear, if you use the class statement, it'll create, oh, I'm sorry, actually not classroom. I'm sorry, that's my mistake. I mean, it'll acknowledge that you have these variables. The intervention is what I have to do. Intervention, sorry, intervention. And the reference is equal to one, equal to one. All right. Yeah, so I'm using a class statement to dummy code intervention, right? To acknowledge that it's categorical or discrete, and then to set the reference level of one. So I'll have these three dummy variables. There's four levels, so there'll be three dummy variables. Okay, there's four levels. We're going to be two versus one. That's one variable. Three versus one. That's two, and four versus one. That's three. Okay, you can set any reference level you want. Okay. So we had classroom, that's our clustering variable, intervention. We have post exercise is equal to intervention. And we have intercept, right? That's going to be our random effect. So let's go ahead and run this. Just make sure I had everything in there right. Oh, and I have an error of some sort. Let's see what I did wrong here. I think I made a little minor syntax error, expecting the following up first flows. Where's the error? Oh, I know. Duh. Forgot something. I thought I got it. Yes, you always have to do this first. All right, there you go. Now I'm going to run it. That's my mistake I make all the time with this one. I forget to put those single quotation marks here. All right. All right. So again, we only have the same covariance parameters. Now here's our X variable. It's a little bit different now because then we have, the intercept, and then we have these different levels of our predictor variable. It shows you the iteration history, how it reduces this -2 log likelihood to arrive at a conclusion here. Let's see. And here's our intercept value. This is what we're looking at here are random effects. And here's our effects of our intervention, right? So 2 versus 1, 3 versus 1, 4 versus 1. And if we look at this, we see only 4 versus 1 is statistically significant, right? So only 4 versus 1 is statistically significant. Here's my parameter estimate, but the other ones were not statistically significant. So this is our model is basically y equals 1.6477, right? That's our intercept value, and then these are the different slope values for the three different dummy variables, right? I mean, you can see that intervention itself overall wasn't statistically significant, but if we break it down into these different levels, we see that there are some areas where there's significant. So it looks like this value really kind of messed it up, right? Messed it up. This effect 3 versus 1. All right, so that's the result with the fixed effect for the intercept. I'm not going to make the slope. I'm not going to make the slope random with this model because this is a little tricky, but you can also relax the slope. And if I wanted to do that, I would just put the variable in here, like intervention in here. But the structure of this with the dummy variables, it's not the same, right? But if you wanted to to test a random slope, you just write the slope name in here. Like if say if this was something different, I'd put it in there, intervention. If it was some kind of a continuous variable in particular, or something that was easier to deal with than this one, I would put it in there. Okay, so now the last thing I'm going to do is we also have data on pre-exercise. So we want to control for pre-exercise. So we can just start making our model like we would make any model. So we're going to add this as a control variable, pre-exercise, right? Then we have intervention as our outcome variable. Here I have intervention as I had it as just another variable, but let's see what happens when I do intervention like I did in the last line. Ref equals 1. All right, see how this works, okay? So we have classroom intervention, reference equal 1. Our model is post-exercise, controlling for pre-exercise. So what's the effect of intervention controlling for pre-exercise, right? We still have the random intercept, right? Random intercept. And we have these output that we want. Let me run this and see if this works okay. Did we get an answer? Let's see. Oh, we did. Okay, great. All right. So what do we have here? Well, let's see. All right. So we have intercept is significant, not meaningful to us, right? Pre-exercise level had an impact on, which we'd expect, had an impact on post-exercise, right? That's something we'd expect. Interestingly, look at this now. The intervention is statistically significant now. Adding this pre-exercise, this is like an analysis of covariance in a way. You're adding this thing that's freeing up some of the variability in post-exercise. You're freeing it away, cleaning it up, and all of a sudden we have more room for a better analysis. And we see that 2 versus 1 is statistically significant, 3 versus 1 is statistically significant, and 4 versus 1 is statistically significant. So all of the interventions are now statistically significant, as is the pre-exercise effect. So controlling for pre-exercise kind of helped us out here. So I mean, I would have done that anyway, because if you have the variable, you definitely want to control for exercise was. I mean, when you do a study where you have pre-test data, you obviously want to control for that because pre-test data will always be related to post-test data, regardless of what you're doing. So if I'm exercising, I didn't start exercising post-intervention. I was probably exercising already. So I have to control for that. Otherwise, we're going to get a false outcome, a false positive result, or even a false negative result in some cases. Okay, so this is your full model here. So the moral of this story is to make sure that, first of all, if you're doing an analysis and there are clusters of data, you should make sure you test whether those clusters have implications on your results. Those clusters will, in a sense, alter your results. So I would do that by testing using this proc mixed. I would test to see if there's an impact of allowing, say, the intercept or even the slope to be random, and see if how does that change the model. And we can use that chi-square difference test, or the -2 log likelihood difference test, which follows a chi-square distribution, to test to see if there's a significant difference. And that'll help us determine whether or not we need to have that random effect in there. And then you proceed as you normally would. So basically, we proceeded as we normally would after we tested for that. That's what we call a multi-level model. All right, any questions from anybody about this? I'm gonna just stop the recording and then I'm gonna ask you guys some other questions. Let me just stop the recording. Uh,
Thank you.
Stop recording. Yes, but all right, let me see. Hold on. Are you stop?